When you're cruising down the highway, sipping a coffee, it's easy to forget that you're hurling a 2-ton metal box over a very uneven planet. Without protection, hitting a single speed bump would send a shockwave straight through the frame, violently launching you right out of your seat. This was a massive problem for early automobiles. Before paved highways, roads were mostly dirt tracks carved by horse-drawn wagons. They were deeply rutted, rocky, and threatened to shake early cars entirely to pieces. To make driving physically possible, engineers had to figure out a way to disconnect the passenger cabin from the violence of the wheels below. The solution they came up with acts a lot like the human body. Think about jumping off a low wall. If you land with your legs locked straight, the impact shoots right up your spine. But if you wear cushioned shoes and bend your knees as you land, your body absorbs the shock. A car's suspension system does the exact same thing, and it has three main jobs. The first is comfort, shielding the passengers and the cargo from the bumps, vibrations, and impacts of the road. The second job is grip. For a car to move, turn, or stop, the rubber tires must be constantly pushed down against the pavement. The suspension presses the wheels into the ground so they don't lose traction over uneven surfaces. As we can see in this three-part diagram, a proper suspension keeps the vehicle's body floating level over a bump, maintains constant tire contact with the ground, and allows the car to steer cleanly and predictably around obstacles. All the engine horsepower in the world is useless if the tires spend half their time bouncing in the air. The suspension is what actually keeps you glued to the road. To understand how this works, let's build a suspension system from scratch. The first piece we need is a spring. When a wheel hits a bump, it moves upward, and the spring compresses to soak up that initial energy of the impact. This graphic shows four main types of springs used today. We have the metal coil compressing, the layered leaf spring flattening out, a torsion bar that twists, and modern air springs using a tough rubber bag filled with air. They all do a great job of cushioning the blow. But there is a strict rule of physics at play here. Springs cannot destroy energy. They can only store it and then release it by bouncing back to their original shape. If a car relied entirely on springs, it would look like this. Every bump would compress the spring, launching the car upward, then compressing again. It becomes a 2-ton pogo stick, bouncing down the road long after the bump is gone. So absorbing the initial impact is only half the battle. We need a way to neutralize all that leftover bouncy energy so the car can settle safely back onto the road. That is exactly where the shock absorber comes in. Engineers often call this component a damper because its entire purpose is to dampen or restrict that endless bouncing motion. Take a look at the inside of this shock absorber. It works like pushing a plunger through a tube of thick honey. As the suspension moves up and down, it forces thick oil through tiny holes inside a metal tube. This creates massive fluid resistance, taking the energy of that motion and turning it into heat. The spring takes the hit, and the shock absorber stops the bounce. Working together, they absorb an impact and immediately settle flat. You can actually test this yourself. If you go to the corner of a car and push down hard on the fender, the car should pop back up and stop immediately. If it bobs up and down 2 or 3 times like a boat on waves, your shock absorbers are worn out. Driving with dead shock absorbers is dangerous. Without that fluid resistance, the tires lose their tight grip on the road, which means your car will take significantly longer to stop when you hit the brakes. We have our spring and our damper, but they can't do the job alone. They need structural helpers, known as control arms and ball joints. These act like metal hinges, locking the wheel in a perfectly straight line while still allowing it to move up and down over bumps. But straight lines are easy. When you steer a heavy car into a sharp turn, physics dictates that the vehicle's weight will try to continue moving straight. This causes the car to lean heavily toward the outside wheels, threatening to roll the entire cabin over. To fight this, cars use a clever piece of engineering called an anti-roll bar, shown here in orange. It's a metal linkage that ties the left and right wheels together. When the car leans to one side in a turn, this bar twists, pushing back on the opposite wheel to keep the chassis perfectly level. Without these sturdy control arms and anti-roll bars, the spring and damper would just bend sideways and snap. These helpers take the stress of the turns, giving you precise, predictable steering. How all these parts are arranged depends on the type of vehicle. For decades, many cars used a dependent suspension, where a solid metal axle rigidly connects the left and right wheels together. Today, most passenger cars use an independent suspension. The advantage of an independent system is exactly what it sounds like. Because the left and right wheels are separated, if the left tire hits a massive pothole, it absorbs the shock on its own without violently tilting the right side of the car. The McPherson strut, first popularized in the 1950s on cars like this Ford Consul, solved this problem by being incredibly compact. It combines the spring, the shock absorber, and the steering pivot into one single vertical pillar that sits right above the wheel. Automotive engineers are always balancing these designs against each other. They have to choose between the heavy-duty, load-bearing strength of a solid truck axle and the refined, agile handle end of independent struts. When all parts work together properly, the results are incredible. As seen in this dashboard challenge, a modern suspension isolates the cabin so effectively that a full cup of water can traverse a rocky dirt road, rippling safely without spilling. These systems also unlock high-performance handling. In racing, an expertly tuned suspension forces the tire tread deep into the pavement, unlocking levels of grip that allow cars to corner at extreme speeds. Look at this wheel assembly once more. It takes a 4-part team: tire grip, spring cushion, shock resistance, and control arm stability. But there is a compromise. You cannot have both racing handling and luxury comfort. Manufacturers strictly tune stiffness to match the vehicle's purpose. Every vehicle strikes its own balance, but no matter what you drive, the next time you smoothly glide over a speed bump, remember that this coordinated mechanical system is working in perfect unison to protect you from the road.